So this is the second video on quantum numbers, and in this video we're going to actually put the different numbers into practice and see how we can come up with sets of quantum numbers for different electrons in different atoms. So we're really linking the numbers to the table. Just a quick reminder, the value of n then represented the principal quantum number, and so that refers to rows or periods. So if I were to number this, I'm actually writing down principal quantum numbers, and so that means any electron in period 2, for example, would have a value of n equal to 2. Remember L, I mentioned, this breaks things down into subshells. And so this is an important link. This is the S block, and in the S block, L equals 0. That's always the case. So beryllium, for example, the last electron that goes in to make up beryllium would have a quantum number L equal to 0. In the P block, L equals 1. And in the D block, L equals 2. And in the F block, L equals 3. So those values of L do not change. So any electron, any inner transition metal electron would have a value of L equal to 3. ML represents individual orbitals. And as I mentioned, we do need sufficient values of ML to account for all the different orbitals in the different shells. So for example, when you have an S block, the S shell has only one orbital, and so there's only one value of ML. With the P block, there are 6 elements across, but there are 3 different orbitals, and so we would need 3 different values of ML for that one. Similarly for the D block, 5 orbitals, 5 values of ML, etc. And so MS is the spin quantum number. It just reflects spin plus or minus 1/2. And again, that's the last quantum number we apply, and then it gives an electron a unique set of numbers. Remember, you could have up to 2 electrons only in a single orbital. So the first 3 numbers in that orbital, N, L, and ML, would be identical, and so you provide a unique set by giving one electron a value of plus 1/2. Therefore, the other electron would have a value of minus 1/2. So let's see how this works when we put it into practice. So sample 1, for n equals 4, what are the possible values of L? Well, if you remember, n equals 4, L equals 0 up to n minus 1, and so L can equal 0, L can equal 1, L can equal 2, and L can equal 3. And so that's it. So we have 4 values of L. And remember what those values of L represent. That represents the number of different subshells at that given energy level. So there are 4 different subshells when n equals 4. For L equals 2, what are the possible values of ML? Well, again, L equals 2, ML equals negative L through 0 to positive L. And so that can be starting with negative 2, negative 1, 0, plus 1, and plus 2. And so if you remember what those values represent, ML represents the individual orbitals. So what that's saying is, because I have 5 values of ML, there must be 5 orbitals in that subshell. Remember L as the subshell. And if you recall from before, L equals 2, that refers to the D subshell, which has 5 orbitals. And there are the 5 different quantum numbers for those individual orbitals. Just a quick little tester. Which of the following orbital designations are incorrect? Give a reason. So 1s, that's fine. N equals 1 is the first energy level. There has to be at least one orbital there. There is one orbital there. It's the s orbital. 1d does not work. And that's because n equals 1. There's only one orbital type. and that's an s orbital. So you don't actually have a d orbital yet. 9s, that's fine. You can have an s orbital at every n value. So n equals 1 to infinity, there will be an s orbital. 3f, well, n equals 3, L equals 0 up to n minus 1. So that's going to be 0, 1, and 2. And so we go as high as, this is a d, yeah, that's a d orbital, L equals 2. And this is saying 3f. So an f designation would need, would have a value of L of 4, not 3. So that is not possible, that particular one. On the other hand, 4f is possible for that very reason. So the f orbitals do not appear until n equals 4, the fourth energy level. 3d, well, that's fine. We just did it up here. 3f, if we look at this one, spd. So 3d works. And 1p, again, does not work. The only orbital present at n equals 1 is an s orbital. Which of the following sets of quantum numbers are not allowed in an atom in its ground state? So n equals 2, L equals 1. Well, that's possible. When n equals 2, L can equal 0 or 1, so that's okay. And ml equals negative 1. Well, that's also okay, because when L equals 1, the possible values of ml are negative 1, 0, and plus 1. So that's good. So that set is fine. N equals 1, L equals 1. Well, that's not possible. When n equals 1, the only value of L is 0. So that's not going to work, that one, that set. N equals 8, L equals 7, ml equals negative 6. And again, that's fine. L equals 7 is the highest value of L when n equals 8, so that's okay. And so the possibilities when L equals 7 for ml are minus 7 through 0 to plus 7, minus 6 is in that range, so that works. That one's fine. N equals 1, L equals 0. Well, that's okay. That refers to an s orbital. There's always s orbitals at any value of n, including n equals 1. But this value doesn't work. The value of ml is 0 only when L equals 0. So this one does not work. Now we get into the part that I prefer and find it a bit more interesting. That's where you come up with the sets of quantum numbers for electrons in a specific atom. So let's look at this first one, give a set of unique set of quantum numbers for the electron in a hydrogen atom in its ground state. Well, hydrogen has a single electron. So there it is. That's hydrogen's electron, and so we're going to have to come up with a set of quantum numbers for that. And hydrogen is found at n equals 1 in the s block. And so n equals 1. The possible values of L, which implies the subshell, are n minus 1, 0 through to n minus 1. Well, that's 0. The possible values of ml, when the value of L is 0, there's only one possibility for L, and that's 0. And finally, we have to give it a spin quantum number. And it doesn't matter what you give it, so I'm just going to give it plus 1/2. Okay, so that's the set of 4 quantum numbers. So that's 4 quantum numbers. That constitutes a set of quantum numbers. 4 numbers in a set. So that's what we're referring to as a set. Okay, so let's go to the next one. And so now we're looking for helium. Okay, unique set of quantum numbers for the electrons in a helium atom. So there's helium, and helium is still in the first energy level, but now we're over on the other side, yet this is not the p block. Helium is still considered to be, the electrons are still considered to be s electrons, and that's because we fill the energy level first. And so if we're going to write the set of quantum numbers, the first one is essentially that electron that made it hydrogen in our first example. And so the second electron, well, it's still at n equals 1. It's still in the s block, so the value of ml is 0. It still can only have one possible value for ml, and that is 0, because it's the same orbital as the previous one. And so we now have to make this set of numbers unique. Notice that the first three numbers are identical. First three numbers means, when they're the same, means it's the same orbital. And we can only put 2 electrons in one orbital, so now we have to make it unique. So now we must pick a spin number of -1/2. And so there's 2 electrons in the same orbital with opposite spins, and that's helium. Give the unique set of quantum numbers for all electrons in a lithium atom in its ground state. Well, here's lithium here, and so we've changed it a little bit. We're no longer in the first energy level, we're in the second energy level. So the last electron, that valence electron for lithium, is going to have a different value of n. That said, we can use what we already did for hydrogen/helium. So those first 2 electrons that make up lithium will have the identical set of quantum numbers as helium. And we're going to add the third electron. And so here, the only thing that's really changed is the value of n. It's in the second energy level. So n equals 2. Well, what are the possible values of L when n equals 2? The possible values are 1 and 0, but we're still in the S block. And if we're in the S block, the value of L is 0. If the value of L is 0, the only possible value of ml is 0, and then we give it spin +1/2. And again, that could be -1/2. But that's the only difference then for the third electron that makes up lithium, the value of n. Let's do another one. So give a unique set of quantum numbers for all valence electrons in a carbon atom. So here's carbon. And so valence electrons really only interested in the electrons that go into the second energy level, because those 4 electrons that go in to make up the valence shell of carbon are the ones we want quantum numbers for. So there's 4 electrons, and they're all in n equals 2 energy level. And so that means all of them, all 4, are going to have a principal quantum number of 2. Okay, so let's break it down. So we're going to look at the first 2 electrons here, which are in the S block. All right, as we build up, as we build across, we're going to put in that electron and that electron. So those first 2 electrons on their way to carbon span the S block. And so when we're in the S block, the values of L are 0. The values of ml are also 0. And the spin would be +1/2 for one of those electrons in the s orbital, and -1/2 for one of the other electrons in the s orbital. And so those are those 2 electrons. And so essentially these 2 would constitute the valence shell for beryllium, but we want to go to carbon. And so with carbon, the last 2 electrons are in the p block. And so we're going to change something here. What we're going to change is we're going to change the value of L. When n equals 2, L can equal 1 and L can equal 0. Well, the higher the value of L, the higher the energy state. P has a higher energy state than s orbitals, and so we're now into a different subshell. And it shows you right on the periodic table that this is the p block. So you know you have to change the value of L. And so that becomes 1. Now here's something we're going to talk about a little later, but there's basically a rule for electron filling. There's several rules, and we're going to come to these, but one of the rules is that we half fill orbitals in a subshell before we fill them. And so by that we mean if I'm going to give a value of ml of +1 to this electron, it means the next electron cannot go into that orbital. And remember, the value of L +1 is a specific orbital. So I have a choice here. I can make it 0 for a different orbital. I could make it -1 for a different orbital, but I do have a choice. What I can't do is make it +1. +1 implies 2 electrons only in that subshell, both in the same orbital, and that is not energetically stable. And so now I have a choice of spin, and I'm going to make it plus 1/2. And here again, I don't have a choice of spin, because as we'll see when we get into these rules a bit later, we have parallel spins when we half fill the orbitals. So plus 1/2, that means the next one would be plus 1/2 as well. And so there are the 4 sets of quantum numbers, unique sets. Notice every set is different, and that set of quantum numbers are the valence electrons in carbon. Well, let's go to sulfur. And so sulfur in its ground state, here's sulfur down here, and so sulfur is in the 3rd energy level, and we have valence electrons again. So we have how many? 1, 2, 3, 4, 5, 6. We're going to need 6 sets of quantum numbers. Well, let's start with the first, again, the S block. Never hurts if you're not sure about things, label the blocks first, because that's going to give you some guidelines. So the S block, we're talking about these 2 electrons. So when it's the S block, I'm just going to put this down to give us a bit of guidance. So when it's the S block, N equals 3 and L equals 0. ML equals 0, and spin, give it plus 1/2. So that's one of those electrons. Well, second electron, N equals 3, L still equals 0 because they're still in the S block, ML still equals 0. Now we have to give it opposite spin because we're in the same subshell, or same orbital. So those are the S. Those are the S electrons. So the electrons in the S block. But now we have 4 electrons, and they're all in the P block. And so the value of N is still the same, still 3. So all 4 of these are going to have a value of N of 3. And the value of L increases from 0 to 1, higher energy state. That's the subshell though. That's the P block. So they're all going to have a value of L equals 1. And now we have to come up with the value of ML. Well, the possible values of ML are -1, 0, and +1. And we have to half fill the orbitals before we go back and pair up the electrons before we fill them. So let's start with -1. So that means this one can't be -1, so I'm going to make it 0. That means this third one can't be -1 or 0, so it has to be +1. So this is what I mean by half filling the orbitals. 3 different orbitals here, each with a single electron. And so I can put in this, go ahead and put in a parallel spin, so I'm going to make it plus 1/2. There's the parallel spins. Now I go to my 4th electron, and now I have to fill one of the orbitals. Any one, doesn't really matter. I'm going to fill the -1 orbital. And so now that orbital's filled. And so now to have a unique set of quantum numbers between this first one and this 4th one, I have to have opposite spin. So this becomes -1/2. And so again, 6 sets of quantum numbers, each one unique, each one pinpoints a different electron, and that's sulfur. Finally, the last one I want to show you is one for vanadium. So here's vanadium. And so this is, again, we are going to cover a rule here that I'm going to talk about in a second in a little more detail later. But here's vanadium, and so if I was to label the energy levels, vanadium certainly looks like it's in the 4th energy level, and a component of it is. That's certainly true. But not all of it is, and I'm going to show you why. But first of all, I just want to draw your attention to this. If we go across each period, looking at each quantum number, so quantum number n equals 1. Remember, that refers to one orbital type. Well, and here it is. It's an s orbital. This would be s, and that actually, even though it's over in the p block, helium, the second electron, it goes into an s orbital. N equals 2. 2 orbital types s. Now we're into the p block, and so all of these would be p electrons. So n equals 2, 2s, and 2p. N equals 3, s orbital type, 3 orbital types present, p across here, so we have 6 elements in the p block, and then there's nothing next to it. There's nothing there. And so that means when we filled the 3p orbitals, we go back here and we start filling the 4s. So there's the 4s. Now, what is this? Well, it's definitely a d subshell, but which one is it? And it's actually 3d. And it's 3d because n equals 3. There are three types of orbitals present, s, p, and d. Just because the d doesn't get filled right away doesn't mean it exists. When it does get filled, though, it's the first incarnation of the 3d. So these are all 3d electrons. So vanadium will actually have electrons in the 3d subshell. And I'll just quickly show you why that is. If we just look at one last way to try to show it, if we look at this is called a energy level diagram, and we're going to come across these as well. It talks about orbital energy. I'm just going to quickly show you why the 3d fills after the 4s. So I'm just going to see if I can line it up here and just draw a line across. So a straight line across. So the straight line through the 4s energy. So at this, in this energy level diagram, it's showing the 4s with a certain energy. And here's the 3d. This is actually the 3d, this line here. The 3d has greater E. And therefore, the 3d fills after 4s. This is known as the Aufbau procedure, or Aufbau rule, and we'll talk about that later. But all you have to remember is really the order of filling is not always through the orbitals. It actually does change. But let's get back to vanadium, and so we hopefully remember that point. We'll get we'll become more familiar with that as we progress. But let's look at these 5 electrons then that make up vanadium. So the first 2 we have to put in are in this area, and so that's n equals 4. So if we're gonna give quantum numbers for those 2 electrons, n equals 4. Well, when it's the s orbital, it's 0. It's 0 for ml, plus 1/2, 0, 0, and then same orbital, the 4s orbital, so it's minus 1/2. So now we're into the d block, but remember, it's the 3d block, so n equals 3. And it's going to be 3 for those 3 different electrons. Now, when n equals 3, the possible values of L are 0, 1, and 2. Highest energetically is the 2 subshell, and we've gone through 0 and 1. The 3p would have a value of L equals 1. So we're into the 3d. The value of L is 2. So each one of those electrons will have a value of ml of 2. They're in the d subshell. Possible values of ml when L equals 2 are minus 2, 0, or minus 2, minus 1, 0, plus 1, and plus 2. 5 different values to accommodate the 10 electrons of the d block. And so here I have a choice. I can pick any number, and I half fill the orbitals. So I'm done there. I have 3 electrons only in the d subshell, so there's my 3, each one in a different orbital, minus 2, minus 1, 0. And I have parallel spins, so I add my last quantum number, spin quantum number. And that's parallel spins. So that would be the set of 5 quantum numbers for vanadium. And that concludes this video on quantum numbers.